In this video, we're going to talk about polynomials. Polynomials are actually something we've already looked at because a quadratic is actually a type of polynomial. So the focus today will be on what a polynomial is and how to name it. So the name polynomial, basically in Latin root here is poly meaning many, nomial meaning numbers. So it means literally many numbers. But in math, it is a function that is made up of at least one term in which all the terms have whole number exponents, meaning their exponents are 0, 1, 2, 3, 4. They cannot be negative. They cannot be a fraction. They cannot be irrational. The degree is what we describe as the largest exponent of the polynomial. So in a quadratic, that would be a 2, and that's why it's called a quadratic. A term is any combination of constants or variables separated by addition or subtraction signs. Okay, standard form of a polynomial is a polynomial that is organized from the highest exponent, otherwise known as the degree, to the lowest exponent, usually ending in a constant, but not always. All right, so how do we name, and by the way, that's always descending order. Everything in math is descending order. So, at least with exponents. So, how do we name that polynomial, right? A polynomial is named first by its degree. And so you can see in this list things you recognize like linear or quadratic, also cubic. There is quartic. So we start with, if there is a 0 degree, we have a constant. A first degree polynomial, keep in mind, if you think about a linear equation, y is equal to 2x plus 3. The exponent is a 1. A constant would be something like y equals any number, so -5. And a quadratic would have a square as the highest exponent. A cubic would have a 3. A quartic would have a 4. And in this modern day and age, that's usually where we stop, but it does keep going. We would have a quintic, a sextic, a septic, an octic, a nomic, right? But typically we just stop here. If you want to learn these other ones, that's great. All right, and then we name the polynomial, then this is the first name, right? And the last name of the polynomial is based on the number of terms. So in this example, we have one term and it's constant. So it would be a constant monomial. But you could have a cubic monomial, right? You could have y is equal to 3x to the third power. And that would be named first by this. So it would be a cubic, right? Be cubic first, and then it would be a monomial because there is one term in this expression. However, if I had something like this, this would be linear first, and then notice that there is 1, 2 terms, so this would be called a binomial, bi meaning 2. And obviously it goes from there, trinomial, quadnomial, pennomial, hexnomial, hepnomial, and so on. And typically we only learn up to quadnomial. So an example of this is if I had y is equal to, we'll do a quadratic, x squared plus 4x minus 3. This would be called a quadratic, and then 1, 2, 3. The technical name for the chapter that we learned previously, this would be called a quadratic trinomial, as opposed to last chapter if we had something like this, right? This would be a quadratic binomial. All right, so I think we should just take a couple look at examples of that and how to name that, and be a good idea for our key terms. So let's take a look at this example right here. So first we're going to determine if it's a polynomial. So let's just determine if it's a yes or no, kind of like we did when we had functions, right? Does it pass the test to be a polynomial or not? So each of these exponents are whole numbers, right? These are whole numbers, so this is a yes. This one, whole numbers, even though there's a 1 there, it's still a whole number, so this is a yes. And this one also, all of these are whole numbers, so it is a yes. So to turn something into a no, let me show you a way to do that. If I did this, let's say I came in here and I made that a -8 in the exponent, right? So if that 8 were negative, or if this 3 were negative, right? So if I did this, and I turned that into not a subscript, let me fix that real quick. If it were an exponent like that, that would make it not a polynomial. It has to be a whole number. Or, right, if one of these numbers, like let's say this number right here became a decimal, okay? That would not be a polynomial. Also, if there were a square root on here, right? If you had the square root, well, square root of 4 would be 2, bad example. But if I had the square root of 3 up there, not a polynomial. Or if one of these was a square root, not a polynomial. So polynomials have to have whole number exponents and also have no radicals in them, because those are called radicals. All right, so now that we know that they're all yeses, let's write them in standard form. Okay, so to write this in standard form, this would be the first one, this would be the second one, and this would be the third one. So this would be 5x to the third power plus 2x squared minus 2x. We'll put them all in standard form, and then we'll name them. This one would be first, and then this one would be second. So this one would be negative. Notice that the negative on the 5, on the coefficient, it comes with it. They're attached. Okay, and if you don't have one at the beginning, it is always, in the absence of a minus, you have a positive. All right, so here we have a little bit more to do. So this will be first, then second, then third, and then fourth. So it would look like this, negative 2x to the 8th power minus 6x to the 6th power plus 5x third to the 3rd power, and then minus 5x. So to name them, right, we look here, right, 3, we go back up to the chart, 3 is a cubic, so that's a cubic. And there are 3 terms, 1, 2, 3, we established that here. So 3 terms is a trinomial. So this is a cubic trinomial. Okay, so here we have a 4. If you look at the chart, 4 is quartic. So this would be a quartic. And there are 2 terms, as we established here. You can see it here, that's a binomial. The last one is an eighth. And if you wanted to, you could call that an octic. But most people, when they get above 4, they just call it like whatever it is. So it would be called an 8th degree, right? That's the degree. So we would call that an 8th degree polynomial. And then we would say the number of terms. And the number of terms here, right, we could call this an 8th degree quadnomial, right, if we wanted to. So instead of saying polynomial, we could have called it a quadnomial. But some people don't even make you learn quadnomial. Some people do, some people don't. So you could call this an 8th degree polynomial with 4 terms. Most teachers make you learn monomial, binomial, trinomial. Quadnomial is kind of hit and miss depending on your teacher, right? But definitely, so this is like the full version of it. And that's why learning the little smaller words makes your life easier. So again, if we wanted to, we could have called this an octic quadnomial, and it would have looked like the other ones. Or if you want to write it all the way out because you don't want to learn past 4, which most people don't, it would look like that. So now we're going to take a look at some operations with polynomials. And I went ahead and did not cover in the notes problems like this. They'll be in your homework. But I mean, I feel like everybody can add like terms, even if it's a minus. I feel like that is pretty easy to go over. So there are some to try in your homework. But I wanted to focus in this lesson on problems that actually are new and unique compared to other chapters. So when we look at this first problem here, we might try to just, we have to multiply 3 things. So what do we multiply and how do we multiply it? Well, you multiply, you got to remember Gelndos, right? You do grouping symbols, then you do exponents, then you do multiplication. And multiplication is done from left to right. So I'm going to start with these 2 right here. So I take those 2 problems and I'm going to go ahead and box that up. You can see I have another box for the second part. So this is my column, so I'm going to put it here. This is my row, so I'm going to put it here. So x times x is x squared. X times 3 is 3x. X times 2 is 2x. And 2 times 3 is 6. So I'm actually just going to write that answer right here. So what do I get? My like terms are always combined right here. So we have x squared as our first term. Then we have 2 and 3, which makes 5x. Then here we have 6. And I make the area model of the box method like this so that the answers come out. And you can go ahead and put the pluses here if you want, right? That's actually positive 5x, and this is actually positive 6. I do that so that it's just easy to write it this way. I know that some of you might want to write it as a column. I just do it this way because it's simple. And then I take this last one over here, okay, and I'll change the color on it so we can keep track of it. And I'm going to put that in the column here. So I'll put the x here and the -1. And this is when you'll really start to see the niceties in the box method or area model. So here I have the same base. So I'm going to add the exponent. So I get x to the 3rd power. Here I have x squared times -1. So -1x squared or -x squared. Here I have x times 5x, so the 5 is really being multiplied times a 1 in the front of the x. And then the x's are the same base, and I add them together to get a square. 5x times -1 is -5x. And then 6 times x is 6x. And then 6 times -1 is -6. And you can see, what I love about the box method is you can actually see that negative going the whole way, so you don't make a careless mistake. But check this out. As promised, your like terms, if you write it in polynomial order or standard form, your like terms are always going to show up on this diagonal. And that sure does make your life easier because you know the x to the 3rd term does not need to do anything. You know the -6 does not need to do anything. Your middle term is actually in order. -1 plus 5 is 4x squared. And then -5 and 6 makes 1x. And it's just so consistent as opposed to a mess. So when you have something like this, the biggest mistake students make is they look at this problem like, oh, this is easy. This is x to the 3rd power plus 125. And it just bears an important mention again that you cannot distribute exponents. It doesn't make any sense. An exponent, so this would be always a problem, and it's always a possible answer, so that kids select it on a multiple choice test, and it's always incorrect. What an exponent means, right, is an exponent actually means to write this down 3 times. So that is our job. Write this down 3 times. And then what we're going to do is once we write it down 3 times, we basically have to do the exact same thing we did on number 1. So if you're watching this video and you want to practice, you might want to pause it and see if I get the same answer I will get here in a couple of minutes. So do that if you want to. I'm going to keep going. So I'm going to start by boxing the first 2, again, left to right. So here we will get x plus 5. The nice thing about this is you just have x plus 5s everywhere, right? So you get x squared. Here you have 5x. Here you have 5x. Here you have 25. I set the next area model up so I can write the answer down right on top of it. Plus 10x plus 25. Then I'm going to put this one, right? We've never done this part of the problem. So I'm going to put that one down on the column here. And so we'll have 5x to the 3rd power. Remember the rule is same base, add the exponents. Here we will have 10x squared. Here we will have 25x. It's really nice to do this method because you can see the x just transferring the whole time. Here you have 5x squared. And then here you have plus 50x. You can choose to put the addition and subtraction signs in if you want. And then 5 times 25 is 125. So you actually see, right, again, you see these like terms on the diagonals. But the other thing you see that's really interesting is the answer that we started with, the 5x to the 3rd power, is the first term, and the 125 is the last term. And that is what we started with, but you're missing all the middle, and that's why that answer is always incorrect. So the middle is to combine your quadratics, so you have 15x squared. And then here you have 50 and 25, which is 75x. So just to hammer home the box method or the area model, you can start to see why it's really good for organization. But if you look at example 3 here, I just can't imagine trying to do this problem by foiling. I feel like it would be a huge mess. So I know that sometimes we put this down as a column and this as a row. I find that on a piece of paper, I usually just put the long one on the top. So maybe this is the long one. Maybe I put it here. I just typically put the long one going across the paper just because of the way that notebook paper works. And if you're using a different kind of notebook paper, or if you're going in columns, maybe you would alter that. So now that we know how to use the box method, we can kind of be a little bit more flexible about what we do. And then I'm going to put this down here. So keep in mind, had I had the exact same problem, right, and the problem had been written like this, so let me move this over here. I mean, if I would have had that problem, I still would have done it this way. And the reason is because of the fact that by doing it this way, it just is better on notebook paper. The answer will come out to the same answer no matter what. All right, so let's go ahead and multiply it. And if you want to know why, it's because of the commutative property, which you learned in Algebra 1, maybe even in pre-algebra, right? The commutative property says the order in which I multiply will give me the same answer as long as I don't change the problem. So 4 times 1 would be 4. X squared and x to the third power, again, same base, write it down, add the exponents. So that would be 5. Here I have negative 3 times 1, so negative 3 and x to the fourth. Again, same base, add the exponents. 2 and negative 2 and 1 make negative 2. Don't forget to put a little 1 there so you don't make a mistake. So 2 plus 1 would be 3. And then negative 1 times that is negative 1x squared. You obviously don't need the 1 if you don't want to put it on there. 3 times 4 is 12. This is an x to the first power, so same base, add the exponents. That will be to the fourth power. 3 times negative 3 is negative 9, and then x to the third power. 3 times negative 2 is negative 6, and then x to the second power. Negative 1 times 3 is negative 3x. One more row. 4 times negative 4 is negative 16. There's no x, so I can just carry down. All of these will just carry down into these boxes. So this would be positive 12x squared. Again, you can choose to put that plus on there if you want. Sometimes I do it just to make sure that I multiply those two negatives together as a check for myself. So sometimes I'll do that, as you're seeing here, to make sure that I remember that the two negatives make a positive. And this is just, again, this is just such a beautiful way to organize this. This is the first term, 4x to the fifth power. My last term is here. That's my constant. And then here are my like terms right there. Here are my like terms right there. And then right here. Here's my next like terms, right? My next term will be this. And then here I have these right here. It's just such a wonderful piece of organization. 12 minus 3 would be 9x to the fourth. And then 16, negative 16 minus 9 minus 2 more would be negative 37 x cubed. So negative 16 and negative 9 would make negative, I think I carried the 1 wrong there. Always double check yourself, right? So this would make negative 25 minus 2 would be negative 27 x cubed, forgive me. Always double check yourself, your brain can play tricks on you. 12 minus 6 is 6, right? And then 6 minus 1 is 5, x squared. And then 8 minus 3 is also 5. So I'm just going to double check those. So 12 minus 3 is 9. Negative 16 and negative 9 is negative 25. Minus 2 more is negative 27. 12 minus 6 is 6, but minus 1 more is 5. 8 minus 3 is 5x. So hopefully, if you haven't learned the box method, hopefully this problem right here convinces you how incredibly important it is. So I hope that you have switched over by this point in the year. So in this example, we're going to take a look at polynomial division, specifically long division. We've already looked at what happens when we divide polynomials, specifically quadratics, or even linear functions when they factor nicely. And today we're going to look at what happens when they have a remainder. And you probably saw this first when you're in elementary school, and it's something that is difficult for students. So I'm actually going to go over an elementary school problem before I go over the high school problem, just to refresh your memory of how this works. So the thing that is being divided itself is called the dividend. The thing that's doing the division is called the divisor, and the answer is called the quotient. And the first thing that's strange is we write the 12 here, and then we make this symbol. It's kind of like it's just a place to work, right? That division symbol. And then we put the dividend inside. And the way that we start this process that's really important is we actually ignore anything that is not going to be a group of 2 at a time from left to right. So when we start this problem, we're just going to take a look at 12 and see how many times it goes into 61. We ignore this temporarily, and we just do this problem. It's really important for the algebra as well. So when we do this, 12 goes into 61 5 times, because 12 times 5 is 60. And then we take that and we subtract it. And that's an important thing to remember too. We're always actually subtracting while we do division to figure out what the next term is. So 61 minus 60 is 1. That's our first remainder. But we don't stop because we have another digit we can carry down. And we carry that digit down, and then we start the entire process over again. But now we're looking at 12 going into 17, which will occur 1 time. Then we do the process again. 1 times 12 is 12. Then we again subtract, and we find our next remainder is 5. So after we know that remainder, we then carry down the next digit, and we get 54. Again, always having something that has the same amount of places as the divisor. So then we start the process again. 12 goes into 54. As a young child, you might have guessed 5 and then had to erase. We're a little more advanced now, so we know that it's actually a 4, because 4 times 12 is actually 48. And that frustration actually doesn't happen in the high school math, because you'll know exactly what to subtract. Unlike in elementary school, you have to guess. So then we subtract this, and when we subtract that, we get our final remainder of 6. And many of you may have learned 2 things. You may have learned to say, well, the answer is 514 remainder 6. Can I tell you that that is probably a bad way to ever think about that, because it's actually the modulus, and we don't write it like that. You might have also been told to put a decimal here and bring down zeros. I'm actually going to invite you to learn something new. You may have learned it in elementary school, but I find it to be a rare thing that students learn in elementary school, is to take the remainder and put it as the numerator of the final answer, and then divide the divisor, and then reduce that. So the actual answer, the quotient as it's called, is 514 and a half. There's really no need to do that decimal thing where you put a dot and drag it down. In fact, if you type it in the calculator, I typed it in Desmos, you can see right here that it comes out to 514 and 0.5, which is exactly right. That's exactly what this is. So that's a really important thing to understand, because that's the only way to do it in the high school version. So in the high school version, same thing. I have my divisor. I'm going to write it out here. If you want to write it in a parentheses, there's nothing wrong with that. And then inside the division symbol, I am going to put the dividend. All right, and then we start the same process. Notice that this is a binomial. So we're going to take this binomial, and we're only going to divide it into this binomial, not into the trinomial. Just like here, there's 2 terms. I want to do this with 2 terms. And the beautiful thing about this is, just like here, how we were really worried about the 60, here we're only really worried about the coefficient. So what you really have to ask yourself is, what do I need to multiply x by to get x squared? Here you multiplied 12 to get 60, and you picked 5. Here we're going to multiply x by something to get x squared, and that is x. Again, x times x squared, sorry, x times x is x squared, but you will have to distribute this because there are 2 terms, and then you have minus 2x. So X was picked to make it a square, then I distribute it to both terms and I write them in their proper location. Then I subtract, but unlike in elementary, I subtract once. Here I'm actually going to subtract both of them. Okay, so I subtract that one and this one. This one will cancel. This one will change to an addition. And this is our first remainder that we get here, which is 5x. Okay, and just like in elementary school, I now draw a line and bring down the remaining portion of the problem. So I put a minus 5 here. And then I start over. And I ask myself again, I only care about the coefficients. Just like in this step, I cared about making 12, 17. All I care about here is making x become 5x, because I want to cancel one thing at a time. This part will be taken care of as you do the problem. So the way to make x become 5x is to multiply it by 5, and then to move this by distributing. 5 times x is 5x. That'll cancel in just a second. And 5 times negative 2, right, is negative 10. Now I'm going to subtract each term, subtract the first term and subtract the second term. This one will cancel. This one is changing to an addition sign. So my remainder is negative 5 plus 10, which is 5. So the reason that it was important for me to review how to do this right here is because it's the only way to do the answer here. The answer is to take the 5, the remainder, right? I'm going to just be consistent and make it red because it was red in the other problem. So I'm going to take that 5 and I'm going to put it right up here, a 5. And then I'm going to put on the bottom of it the divisor, which is x minus 2. Now, unlike in elementary school where I didn't need to do anything, since this is an algebra problem, I do need to put a plus here. And if it were negative, you'd put a minus. So the overall answer for this problem is x plus 5 plus the remainder divided by the divisor. And that's the easy process. One thing that I noticed as I was doing it that some people have trouble with is, why did I skip this thing here? The reason I skipped it, and it's a little, we did not put that 5, maybe I should move it over to there, because we did not put a number on the 6 either, because there are two places here. So we put our first quotient answer over the second value. So 2 things, I put the 5, 2 things over. Here I have a binomial, so I start at the binomial step. If I were dividing by a trinomial, I would actually put it here. So why don't we take a look at another example? Okay, so here we go. We have this one again. This one's a little different because there actually are things missing. So up here, we have everything we would need to have in our polynomial. But down here, there are terms missing. And the reason that this is important is in elementary school, like let's say this was 2,103. You actually have this to hold the tens place. But here, do you see how there's no x? You have to actually include it. So the first thing you're going to have to do is you're going to have to rewrite the problem to include the missing terms. And you could rewrite it at the beginning if you want, or you can just do it when you divide. So I'm going to rewrite the divisor as x squared plus 0x plus 3. And yes, you have to do that because things won't line up otherwise. Then I'm going to divide that into, notice I'm missing the x to the third power plus 3x squared plus 0x minus 3. Okay, so notice that I'm missing those terms. The reason we do that is things will not line up if you don't put those placeholders in. Notice also in this case that I'm going to be dividing 3 things, so my first answer is actually going to appear right here because of the fact that I have a trinomial, so my answer will occur on the third term. So this looks like a whole lot to do, but you don't have to do a lot. Again, all you care about is making this coefficient become this one. So how do I take x squared and make it become an x cubed? I use an x to the first power. And then what I'm going to do is I'm going to multiply, distribute this times each term. And that's where that placeholder is really important. If you don't put that placeholder, things will be jumbled. But watch how nicely it organizes. X times x squared is x cubed, right? And then x times 0x is 0x squared. X times 3 is 3x. Okay, and then I will subtract each of these terms. Instead of subtracting 1, I'm going to subtract 3 different things, giving me my first remainder. These things cancel, right? 3 minus 0 is positive 3. Remember, we are subtracting, but we're subtracting positive 3 minus 0. Then I have 0 minus 3, which is negative 3x. And then I'm going to drop down this negative 3. So this is my, it's actually good to have a trinomial because there's less work because we started all the way over here. So again, don't focus on everything. Just focus on making x squared become 3x squared. I need to multiply by 3. I then multiply each of these things by 3. Okay? If you need to use the box method over here to figure that out, please do. It is kind of a mess, right? So we get 3x squared. Then here we have 3 times 0, which is 0x. 3 times 3 is 9. Now we will subtract each of these individually. This cancels. This is a negative. This is a negative. So we'll get our answer down here of negative 3x. Again, this is just a placeholder, so if you want to scratch it out, you can at that step. 3 minus 9 is negative 12. And this will be our remainder that we'll put right here, negative 3x minus 12. And then we divide that by the divisor, which was x squared plus 3. And we put a plus sign here. And a lot of students will say, why don't you use a negative? You've got to be careful. Here is one answer, x plus 3 plus negative 3x minus 12, okay, over x squared plus 3. It would be inappropriate to combine these and make it a negative. The way that you would have to do that is you would have to factor a negative 1 GCF out to make it 3x plus 12. And then you would combine those two together. So you would get x plus 3 minus this expression, because you just combined those things, removing it. So you get 3x plus 12 divided by x squared plus 3. So this is the fully correct answer. And on an SAT or a multiple choice test, I guarantee this answer will show up on an SAT. Or an SOL if you're in the state of Virginia, right? However, the other answer, where you did the plus and you left that part out, I mean, that would be acceptable. I wouldn't mark it wrong on my test because I'm glad you learned how to do long division. But you've got to understand that you may have a multiple choice, and on my test, this question may be a multiple choice, and this is the answer I'm going to present. So you really need to understand that, how that works, how that negative comes out as a GCF, right? GCF factoring is super important. It shows you how to properly simplify expressions. So long division is one of those things that it sure would be nice if there was a shorter, more I don't know, less complicated way to do it. And sure enough, there is. And it has a weird name called synthetic division, which makes some people think that it's actually, the name scares them. But it's actually a simplification of long division. But being a shortcut, it actually has a few restrictions. The first thing is it only works with linear divisors. Right? Divisor meaning the thing I'm dividing by. So notice that both of these have an exponent of 1. Okay? Both the dividend and divisor must be in standard form. That's nothing new. And all missing terms must be rewritten with a 0. Nothing new. That's really important to understand both those things. Okay? If the divisor has a coefficient other than 1, you have to, you must divide the quotient by the divisor's coefficient. What that is saying is there's a problem when you have like a number in front of the x. So the first two examples don't have that, and then we'll look at problems. So let's learn the process. So the process is And what makes long division difficult is the fact that you have to subtract a lot. That's actually the place that students make errors. So what somebody thought up before we had calculators and before we had the internet a long time ago, what happened is they figured if they set the divisor equal to 0 and solve, right? If I solve that, I would get x is equal to 2. And if I use that number instead of this number, I don't have to subtract, I can now add. And so to denote this differently, they flipped the division symbol upside down. And to make it even easier, they got rid of the variables and just used the coefficient. So here they just used the coefficient of 1. So they put a 1 right here. Here they use 3. And here they use -5. And some teachers and students will actually label this column as the quadratic column, the x column, and then the constant column. That's very helpful. And so what you do is inside this inverted synthetic division box, you add everything that you have in here. So you start from left to right. 1 plus nothing is 1. And then just like regular division, you multiply. 2 times 1 is going to give you 2. And then you add. 3 times 2 is 5. And then you multiply. 2 times 5 is equal to 10. And then you add -5 and 10, which gives you positive 5. So what is the answer? So the answer comes out also with no variables on it. So what happens when you divide is you reduce this column by one exponent for the answer. So if this is a square, this will be the x in the answer. And if this is an x, this will be the constant in the answer. And if this is the constant, this will be the remainder in the answer. So the answer comes out as 1x, this is the quotient, 1x plus 5, and then plus 5, and it's a remainder, so same rules. The remainder will be this number, and then divided by the divisor. And I don't know if you realized it, but we actually just did the exact same question we did with long division. So let's see if we got the same answer, x plus 5 over x minus 2. And if I go back to the problems we just did, right here, same problem, look what we got, x plus 5 over x minus 2. My advice, this process is very easy, but because it's so devoid of letters, students really need to see it again. So I would pause that video, I'd go back a couple of minutes, and I would watch that again. So let's take a look at the next example. So the next example, again, here's the process. We set the divisor equal to 0, which would give us x is equal to -1. We then put that -1 on the outside of the divisor symbol, the division symbol, which is now inverted. We take the coefficients of this, but we have to be careful about this rule. It has to be in standard form, and if you're missing a term, you have to put a 0 there. Students do a really good job at that when they do long division, but for some reason when they come in here, it's like they don't see the fact that we're actually missing a 0x right here, right? Sorry, 0x squared. So when I label this out, I want to start with the fact that I have a cube, and that's why labeling this helps. And you want to have something for each column for the entire polynomial, even if that column is actually a 0. So in this problem, I have a 1 for the cube column. I have a 0 for the quadratic column. I have a 3 for the linear column, and I have a -5 for the constant column. Inside the box, we are going to add. So 1 plus nothing is 1. -1 times 1 equals -1. 0 plus -1 is -1. -1 times -1 is +1. 3 plus 1 is 4. -1 times -4 is -4. -5 and -4 add to -9. To figure out the answer, you reduce this column by one exponent. So this in the answer is x squared. This is the linear. This is the constant. This is the remainder. So the actual quotient is 1x squared minus x plus 4 minus the remainder of 9 over the divisor, which is x plus 1. So it's almost like you're doing this in code, and once you learn the code, it makes division much easier. But there is an important caveat right here about what happens if I stick a number right there. So let's take a look at what happens on that. And by the way, this problem is impossible because of this, and I'll talk about that in a minute, but you can already see that. So let's take a look at this one. This one, when I set it equal to 0, I don't end up getting, I don't have an integer. I have a, right, I'm going to subtract 1, so I would have, I'll just do it right here, 2x plus 1 is equal to 0. So let me actually show you what we get before I start talking about it. So we would subtract 1 on both sides, we get negative 1, and then we divide by 2, so we end up getting negative 1. That, of course, is a rational number. Many people call it a fraction, and that's where the problem lies. It's not impossible, we just have to be careful what that means. So we take negative 1/2, we draw our inverted division symbol. It looks like we have a cube, so I'm going to label that I need to have a cube, I need to have a square, I need to have an x, I need to have a constant. I have a 2 for my cube, I have a 9 for my square, I have a 14 for my x, I have a 5 for my constant. So I'm going to add inside the box. 2 plus nothing is 2. And then don't get afraid, I'm not going to provide a fraction that's complicated. Negative 1/2 times 2 is negative 1. 9 plus negative 1 is 8. So you can see what I did here where I gave you an example where the fraction plays nicely, so that's not the problem. Negative 1/2 of 8 is negative 4. Add this together, and that'll give you 10. And then multiply half of 10 negative, that will give you negative 5. And then 5 plus negative 5 is 0, which means I have no remainder. So then you label this by starting with the cube and saying the answer is reduced by 1, x squared. This will be reduced by 1, so x. This reduces by 1, so constant. This is remainder. So your answer comes out to the quotient, at least you think the quotient is, it is 2x squared plus 8x plus 10. And this answer is actually off by a factor of, guess what, 2. So you got to think about this as saying you need to divide the answer by 2. It's always going to be that way. And let me show you how obvious it is. If I try to take 2x and make it become 2x cubed using long division, what do I need to multiply this by to get this? I don't need the 2, but it's in my answer because the 2 is already there. So you just have to remember, if you have a fraction for long division, you have to come back and divide by the denominator. You don't care about the negative or the 1. You just care about the denominator. And the real answer is actually x squared plus 4x plus 5. That's the real answer. It has to be reduced by the denominator. And then the last really important part is this. If you have a divisor that is quadratic or higher, you can't do it. You have to go back now, unfortunately. You're going to have to do long division. You're going to need to make sure you put that placeholder for the linear term in there. You're going to need to make sure you do the entire thing. This is very important for later in the polynomial chapter because division is extremely useful for reducing problems. But you can't use the shortcut synthetic division method on a quadratic. So you have to do this using long division. Okay, so just remember that. Synthetic division is great, but it only works when the coefficient has an exponent of 1. So now that we've covered the long division, I wanted to come back and just address something that has occurred in other chapters in this class that does show up with long division. And that is that this remainder And keep in mind that we're dividing by this. So another way of thinking about this is that this is the denominator, and it shows up on the remainder. It produces a domain restriction. So remember that domain restrictions are where the denominator, right? The denominator cannot equal 0 in any problem. So if I set x minus 2 not equal to 0 and solve that, I will see that this problem has a domain restriction that x can never equal 2. I like to think of those as anti-solutions or anti-roots. You know, you do this zero product property quite frequently to find solutions, but this is finding where a solution is impossible. Meaning this is my answer, but if I put 2 in here, I'd have 5 over 0, which would make it undefined. So each of these problems has one. I'm going to go back through now and take a look at each of the domain restrictions for each problem. So this one that we did here, the domain restriction would be that this denominator right here, or it's actually the divisor, keep in mind that the divisor is the denominator, is that x plus 3 can never equal 0, because that's the denominator of the remainder or the divisor. So I would subtract 3, and then something interesting happens here for the first time for domain restrictions, but it happened in our quadratic chapter, that you end up taking the square root, and you end up getting that the domain restrictions are imaginary. And what that is telling you is that you actually don't have any, because right from the quadratics chapter, this would come out to plus or minus the square root of I root 3. So I don't actually need to include any domain restrictions on this problem because they're imaginary, and imaginary domain restrictions would not cause an actual problem in the set of real numbers, which is what you reduce algebraic expressions over. So this would be the answer, and this would have a domain. Remember, the domain refers to the xy axis, and so there would be no interruptions on this xy axis with this. This does not show up here, so this would be the answer with no domain problems. So when we look at this problem was the same as the one we looked at earlier. Literally, it's the same problem. So x could not equal 2. This one, you would have that x plus 1 could not equal 0. So x can never equal -1 here. So I just put a little semicolon and say this is my answer, but x can never equal -1. And then for my last one here that we did, that we had to divide, remember we had to do that division because of this little rule that says if you have a coefficient that is not 1, you have to divide by that coefficient at the end. There's a mix match, of course, that can't be fixed. This one doesn't. This one's interesting because it appears to not have any domain restrictions. The domain restriction is still that x could not equal -1/2. Now, why is that? Because the divisor, even though there was no remainder, because we divided by this, this is still a denominator. So that domain restriction is still applicable. And so notice that when you do synthetic division, the domain restriction is actually the same as the number you have out here every time. So that number is what you use with synthetic division, but it also is the domain restriction because it comes from the divisor. Now this problem here we didn't end up doing because it was long division, but it is the same problem we looked at here. I just copied it. And that one is the whole situation that we have where we have an imaginary domain restriction so it doesn't affect the problem. Domain restrictions are important. They come up in a lot of chapters, and eventually there's a chapter where it comes up in every problem. So please make sure you look through that, maybe watch this part again, and make sure you understand how domain restrictions work for division.